Hi everyone. In today's video, we're going to cover section 2.2, the inverse of a matrix. So you've heard the term inverses in various math courses in the past. We have like the additive inverse. If you add 5 and negative 5, you get 0. The additive inverse of a matrix is not that interesting because you just negate every entry. The way that we do addition, that's nothing special about that. But because of how we multiply inverses, the multiplicative inverses is much more interesting in how we find it and all that. With numbers 5 times 1/5, we know that that's the multiplicative inverse. We want to get 1 as the product there. So in the case of invertible matrices, we want the inverse to be the identity matrix. Okay, so an invertible matrix, n by n, notice it has to be a square matrix. Then A is said to be invertible if there is an n by n matrix C, such that C times A equals the identity and A times C equals the identity. So the multiplication has to be verified in both orders because multiplication with matrices is not commutative. Okay, so in that case, then we identify the inverse as A inverse, A with -1 exponent. Okay. And what it says in the second sentence is that inverse of a matrix is unique, because if B were some other inverse of A, then you should read through that chain of equalities to see why B and C would have to be the same matrix. So that what it's basically saying is that another inverse of a matrix cannot exist. Just like 5 only has one multiplicative inverse, a matrix A only has one multiplicative inverse. We'll do a quick example. Given these two matrices A and C, and we're going to ask the question, are capital A and C inverses of each other? Okay, and we do that by multiplying A times C and C times A. We have to verify that product in both orders. So A times C, we multiply 2, 5, -3, -7 times -7, -5, 3, and 2. And going again row by column, first row, first column gives me the first entry in that product. 2 times -7 is -14, and then we add 15 and get 1. Going first row, second column now. 2 times -5 is -10, add 10 is 0. -3 times -7 is 21, and then -21 is 0. And then the last row and column would be +15 minus 14 is 1. So hey, we get the identity when we multiply A times C in that order. The same thing happens with CA. I'm not going to go through every step of this product. I'm just going to write down that it equals the identity, but I would encourage you to check and see and verify that you do in fact get the identity. -3, -7, 1, 0, 0, 1. Again, you should check that on your own, okay? But you do end up with the identity. So then the answer to that question would be yes, A and C are inverses of each other. And we could write A is equal to C inverse, and C is equal to A inverse. There we go. Now we encounter our first theorem, which gives us our first technique for how to find an inverse of just a 2x2 matrix. So this formula over here is just for a small 2x2 matrix. Okay, and what we verify first is that this product, AD minus BC, is not equal to 0. And if that is not equal to 0, then we say that A is invertible, and its inverse is given by this formula. So we take 1 over that AD minus BC, and then reorient our 2x2 matrix this way. We switch the A and the D entries and negate these two entries. And then whatever that fraction is would distribute into our new 2x2 matrix. And that is that's the first technique for how to find an inverse. And we're not going to go through a proof of why this is true. For now, we'll just treat it as a formula. We're going to look at some other proofs a little bit later in today's video. And let's look at an example where we apply that formula from the previous slide. We're going to find the inverse of this matrix A, and our steps are as follows. First, we're going to find A times D minus B times C. Verify that that is not 0. Okay, this is A, B, C, D. All right, so we're going to take 3 times 6, which is 18, minus 5 times 4, which is 20. 18 minus 20 is negative 2, which is non-zero. Therefore, A inverse exists. All right, and then to write down A inverse, A inverse is equal to, we're going to take 1 over that AD minus BC number times, remember, A and D switch, 6, 3. The other two entries negate, negative 4, negative 5. And then we will just simplify, distribute our negative 1/2 into the fraction, into the matrix. So that's a scalar. Multiply by every entry. We get a negative 3 there, a positive 2 there, a positive 5/2, and a positive 3/2. Okay, so there is our A inverse matrix. And I could verify that those two matrices are inverses of each other by multiplying A and A inverse. You could check the entries if you want to. I'll just point out like the first row in column 3, 4, negative 3 and 5/2. 3 times negative 3 is negative 9. 4 times 5/2 is positive 10. Negative 9 add 10. Hey, you get 1. The other entries would also check out. Now we get our second theorem of the section. Theorem 5 says that if A is an invertible n by n matrix, then every B, for each B in Rn, each B in Rn, the equation Ax equals B has a solution x equals A inverse times B. So this says that if A is invertible, every B has a solution, right? That we're never going to have an inconsistent system, and that's what it looks like. X equals A inverse times B. And we'll write a short proof of this theorem, again, to get you exposed to the theory and see how, proofs in math work. And we're going to start our proof out by saying take any B, any vector B in Rn. Then we're going to say if Ax is equal to B, then A inverse times Ax is equal to A inverse times B. And I know that that inverse exists because we're told that A is invertible. So I know this because, B/C for because, A is invertible, E-R-T-I-B-L-E. There we go. And then, working with that equation, A inverse times A is equal to the identity. If they're inverses of each other, their product is the identity. So we have the identity times X is equal to A inverse B. And then if I multiply the identity by a vector, it doesn't change the vector, so we have that X is equal to A inverse B. Okay, so that's a really short proof of how that works. That doesn't show the uniqueness part. We would need to say a little bit more to say that it's unique, but I just wanted to kind of show where that, or how that works. In this next example, we're going to use the previous theorem to answer a question. The question is referring to the matrix from the earlier example. In example 2, we were given that A is equal to 3, 4, 5, and 6. Notice how my coefficients there, 3, 4, 5, 6. So this system uses the same coefficient matrix as the previous example. And in that example, we found that its inverse, A inverse, is equal to, let's see, it was negative 3, 2, 5/2, and negative 3/2. All right, and so we can use that matrix to solve this system. We're going to say, all right, well, we know that the solution based on that theorem is X equals A inverse times B, that right vector, the 3, 7 vector. So we take our inverse, negative 3, 2, 5/2, negative 3/2, and I'm going to multiply that by 3, 7, by that vector. In the first entry, no fractions to worry about, so let's see what we get there. Negative 9 add 14 is 5, so that was row to column, negative 9 plus 14. And then second row times that vector is, let's see what we get here. 15 halves minus 21 halves is negative 6 halves is negative 3. You should definitely use your calculator if you're not certain about the fractions there, but I'm reasonably confident in my skills. So that's what we get there. So that's our solution, right? That's our solution vector, x equals 5, negative 3. Now, since we introduced this new topic of invertible matrices, let's talk about its properties. Theorem 6, if A is invertible, then its inverse is invertible, which should make sense. And if you invert the inverse, you get the original matrix A. If you have two invertible matrices, their product is also invertible, and the inverse is the product of the inverses in the reverse order. So if I have AB in parentheses, the product first inverted, that is equal to B inverse times A inverse. The same thing happened with transposes in the last section. And then if A is invertible, its transpose is also invertible, and the inverse of its transpose, the inverse of A transpose is the transpose of A inverse. So it looks like that. The notation is easier to understand than the sentence sometimes. Okay? So there's just a few properties for inverses. All right, our next definition is that of an elementary matrix. An elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. And this example gives us three different kinds of elementary matrices. Okay, and so there are three operations. We had a replacement operation, an interchange operation, and a scaling operation. And if you look at E1, E2, and E3 in the example there, I made it a little bit bigger to see. They are each, you can kind of hopefully tell by looking at them, which elementary row operation made them, I guess I'll say. So E1, for example, notice the negative 4 there, that had a replacement operation done on the identity. Negative 4 times row 1 add row 3 would produce this matrix from the identity. E2, row 2 and 3, switch them, and that produces E2. E3, scale row 3 by a factor of 5, would produce E3. Okay, so that's what that is. And now the next step in the example is we need to find these three products. So I'm going to take E1 times A. E1 says 1, 0, 0, 0, 1, 0, negative 4, 0, 1. And we're going to multiply it by that matrix A. A, B, C, D, E, F, G, H, I. And what you'll notice in going through this product is that when I take row and column, each row and column, all those entries, and multiply them and see what we produce here. 100 times the ADG column gives me just A. 100 times the BEH column gives me just B. 100 times the CFI column spits out a C. Okay, so it doesn't change row 1. Similarly, if you go through the middle column, use a different highlighter here, or the middle row, excuse me, to each of the three columns on the right, it produces D, E, F. Nothing changed. Finally, if you go through row 3, that's the different row, to each of the three columns, this is going to get a little bit messier, but this would produce negative 4A plus G. Negative 4A plus G. Negative 4B plus H. Negative 4B plus H. And negative 4C plus I. Okay? And so what we're showing in this example is that, like, previously, we've been writing negative 4 times row 1, add row 3, store the result in row 3. Okay, that's how we write our row operations. What these elementary matrices are showing is that row operation, I can also express it as a product of two matrices. So instead of writing out the row operation, I can say, well, I just multiplied those two matrices, the elementary matrix times whatever my matrix is. Okay, so that's what we're kind of seeing with this example. In a similar fashion, if I multiply E2, 0, 1, 0, 1, 0, 0, 0, 0, 1 times my ABC guy, C, D, E, F, G, H, I, that produces, well, 0, 1, 0 going through my matrix is going to put a DEF up top. 1, 0, 0 multiplying through the matrix on the right is going to put an ABC in the middle, and 0, 0, 1 going through the matrix on the right and doing that multiplication is going to produce GHI. And so that product is, well, it switched rows 1 and 2. So we've switched rows 1 and 2 by multiplying our elementary matrix times the matrix A. Lastly, you can hopefully kind of guess what's going to happen with this last one. 1, 0, 0, 0, 1, 0, 0, 0, 5. It looks like we're just going to scale our matrix A, ABC, D, E, F, G, H, I. And that is, in fact, what happens. Row 1 multiplies through that matrix, gives me ABC. Row 2 multiplies through that matrix, gives me a DEF. Row 3 multiplies through. You can see the zeros aren't going to give me anything except the 5 gives me a 5G, a 5H, and a 5I. And so that scaling operation we can express as a product of two matrices, one elementary matrix and our given matrix A. And that has a lot of significance in just a second when we look at our next really important theorem in this section. Two quick points before we get to that theorem, though. Each of those elementary matrices E are themselves invertible, and the inverse is the elementary matrix of the same type that transforms E back into the identity. And then I'll leave you to read the second sentence, the second point there if you so choose to. And then here's an example, kind of verifying the first bullet point from the previous slide. We want to find the inverse of this E1, okay? And the inverse, E sub 1 inverse, what that looks like is what matrix would I need to turn this, or what row operation would I need to turn that E1 matrix back into the identity, right? And what it is 4 times row 1, add row 3, store the result in row 3. That would get this to look like the identity, right? So if you perform that operation on the identity, what you get is 1, 0, 0, 0, 1, 0, 4, 0, 1. Okay? And that, according to the bullet point on the previous slide, is the inverse of E1. Okay, and you can verify that with some multiplication. Multiply them in both orders, and you will see that you produce the identity as a result. All right, now we get to Theorem 7, and Theorem 7 is kind of a big, important theorem in this section. And what it says is that an n by n matrix A is invertible if and only if it is row equivalent to the identity. So if row operations on A yield or produce the identity as a result. And then in this case, any sequence of elementary row operations that reduces A to the identity also transforms the identity into its inverse. So that's the really significant, that's why this theorem is so important, because it tells us how to find inverses, okay? And we'll see that as we go through the verbiage of this proof. And I encourage you to listen to me kind of walk you through the proof, read through my notes again. You can read through it in the book also. Watch someone else on YouTube do the proof, but it's a really important aspect of this course is to understand the theory that underlies what all of the computation. Okay, so let's start this proof. Okay, and this is an if and only if. Where is if and only if? Right there. This is an if and only if proof. So we have to go in both directions. All right, and so we'll start out by going in the forwards direction for this proof, and we're going to say let A be an invertible matrix. So that's the left-hand side. A is invertible. So we start out by saying let A be an invertible matrix. Let A be an invertible matrix. Sorry about my terrible handwriting. And what we have to do is show that A is row equivalent to the identity. Okay, and the way that we do that, we say then, since AX equals B has a solution for all B. That was an earlier theorem. For all B, AX equals B has a solution for all B. That means that A has a pivot. A has a pivot position in every row. And that comes from theorem 4. I'll write it over here in parentheses. That comes from theorem, THM, for theorem 4 in section 1.4. Section 1.4. Theorem 4, section 1.4 that said that if AX equals B has a solution, then A has a pivot position in every row. Now, what's important next to say is because A is square, right? It is n by n is a square matrix. Where do the pivots have to be? The pivots must be on the diagonal. Right? The pivot positions have to be on the diagonal, and that gives us what we need. Thus, A is row equivalent to the identity. Okay, and that is a proof of the forward direction of this theorem. All right, now we move into the backward direction of the theorem. So let me just draw a line kind of separating it. Now we're going in the backwards direction, and we're going to say suppose, so we assume the end of the proof, what comes after the if and only if. Suppose A is row equivalent to an n by n identity matrix. Okay, then what we say next, since each step of the row reduction of A corresponds to left multiplication by some elementary matrix. To left multiplication by an elementary matrix. An elementary matrix. Okay, so that's each step of the row reduction corresponds to some multiplication problem. Then there exist elementary matrices E1 through EP. E1, E2, E3, E4, etc. Oops, that should be a capital E. Let me fix that. E1 through EP, such that A is row equivalent to E1 times A, right? So I perform the first row operation or multiply by the first elementary matrix, and that would be row equivalent to E2 times E1 times A. I'm multiplying by all of these elementary matrices, and eventually, when I multiply by the last one, EP times all the ones that came before it, EP minus 1 times etc., all the way down to E1 times A, that is equal to the identity. Okay, so again, think of these elementary matrices each as doing that row operation step, okay, ultimately producing the identity as a result. Okay, so what that means, or we can just say that E1 or EP through E1 multiplied by A is equal to the identity. All right, so we're getting there. This is the more challenging part of the proof to comprehend, but it's also the really important part of the proof because it tells us how to find an inverse. So we're almost there, though, so stick with me. Since the product of invertible matrices is invertible, is the next thing I'm going to write. Since the product of invertible matrices, matrices is itself invertible, then we can say that EP through E1 inverse, right, the inverse of that product, times EP through E1 times A is equal to EP through E1 times the identity. Okay, so where did I get that from? I'm taking this equality up here and left multiplying by EP through E1 inverse. Oh, and I left off my inverse notation there, so let me add that in. Sorry about that if that confused you. I'm left multiplying both sides of that equality by EP through E1 inverse, by all of those elementary matrices multiplied together, but they're inverse. And in doing that, I can take the left-hand side here, EP through E1 inverse times EP through E1. That's the product of invertible matrices. So that would give me the identity times A is equal to EP through E1 inverse times the identity, or A is just equal to that, EP through E1 inverse. All right, so let's try to draw this to some sort of conclusion here. If I haven't lost you yet, hopefully. So we're going to say thus, A is invertible. A is invertible since, I can spell today, since it is the inverse of an invertible matrix. So notice this matrix, that product is invertible, so A is invertible of an invertible matrix. And that is theorem 6. And also, here's the important part, also, A inverse is equal to EP through E1, that set of matrices inverted. EP through E1 inverse would give me the A inverse. Okay, so that is just EP through E1 times the identity. Okay, and the significance of that, which I'm going to say it a couple more times probably, is that to find the inverse of a matrix, I perform the same set of row operations on the identity. The same set of row operations that reduces A to the identity also transforms the identity into its inverse. That's what's cool about this theorem. And so that is the significance of the proof of that theorem, is that it tells us how to find identities. If we augment our matrix A with the identity I, those same row operations that reduce A to the identity simultaneously change the identity into A inverse. So we take that A augmented with the I identity and produce that as a result. And if I don't get that, if I don't get the identity on the left-hand side, then A doesn't have an inverse. So let's use that algorithm on this matrix A and see what we get, okay? And let's go. So we're going to augment 0, 1, 2, 1, 0, 3, 4, minus 3, and 8 with the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, and so let's perform some row operations. I'm not going to write down every operation, but I'll say them out loud. And I could just punch this into my calculator, but I think I want to go through each step for this example. So our first row operation is to switch rows 1 and 2. 103, 0, 1, 0. 0, 1, 2. Oops, 0. Yeah, that's right. 0, 1, 0, 0. 1, 0, 0. Sorry, stumbled a little bit there, but I think I'm okay. and then 4 minus 3 and 8, 0, 0, 1. So that was our first operation, switch rows 1 and 2. Second operation, we're going to do negative 4 times row 1 and add row 3, leaving row 2 alone. Like that. There we go. Leaving row 1 alone. Like that. There we go. Negative 4, add 4, I get 0. Let me change color for this. There we go. 0. Negative 4 times 0, add negative 3, stays the same. Negative 4 times 3 is negative 12. Add 8 is a minus 4. Negative 4 times 0, add 0. So I'm just going across the top, right? Negative 4 times 1 is negative 4. Add 0. Negative 4 times 0, add the 1. There we go. So that's our first row operation complete. Okay, now moving on to the next operation. We're going to say that that is row equivalent. All right, what am I doing next? I'm going to keep row 1 the same. 103, 0, 1, 0. I'm going to keep row 2 the same because I have those two pivots in place. 1, 0, 0. All right, my next operation is I'm going to take, what am I going to do? I'm going to do 3 times row 2 and add row 3. 3 times 0 plus 0. 3 times 1 is 3, minus 3 is 0. 3 times 2 is 6, minus 4 is 2. 3 times 1 is 3, plus 0. 3 times 0, add negative 4. And 3 times 0, add 1. All right, so that's our next row operation complete. Unfortunately, in our next step, we're going to have a fraction. I'm going to scale row 2 by a factor of, or row 3, excuse me, by a factor of 1/2. So let's do that. Row 1 is staying. Row 2, 1, 0, 0. And then row 3, 0, 0, 1. 3 halves, negative 2, and 1/2. Okay? And then, what are we going to get next? I'm going to go down a little bit more so I can give myself lots of space. Now we go back up the stairs. We use the bottom pivot to eliminate everything that is above it. So now in this step, the only row that stays the same is the bottom row. 3 halves, negative 2, 1/2. All right, so what do we get here? Or what is my row operation, I should say? We want to use this 1 to eliminate the 2 that's above it. So negative 2 times row 3, add row 2. Negative 2 times this, add that, is 0. Negative 2 times this, add that, is 1. Negative 2 times this, add that, is 0. Negative 2 times this is negative 3. Add that, is negative 2. Negative 2 times this is 4. Add that. Negative 2 times this is negative 1. Add that. And there you go. All right. One more operation. I'm going to change colors again. And what are we doing here? Now we're going to take negative 3 times the bottom row. Negative 3 times this. Add that. Negative 3 times this. Add that. Negative 3 times this. Add that. 0. Negative 3 times this. Uh-oh. That'd be negative 9 halves. Add that. Negative 9 over 2. Negative 3 times this. 6. Add that. 7. Negative 3 times this. Negative 3 halves. Add that. Okay. A lot of work. Let's take a look. So, did we get the identity on the left? The answer is yes. And what happened, what that produces, what those row operations produce on the right is A inverse. So A inverse is equal to negative 9 halves, 7, negative 3 halves, negative 2, 4, negative 1, 3 halves, negative 2, 1/2. That is the inverse. Cool. So that is the end of section 2.2. Thank you very much for listening. Get started on the homework. Email me with questions. See me with questions if you have any. And have a wonderful day.